what we studied before about partial derivative equations, and we said this is type of equations that we want to compute to integrate these equations or by compute the solution of the derivative of some functions. But this function is defined in terms of more than two independents or two independent variables. Like for example, du over dx and du over dy. So not only a single derivative like what to study before. So in this case, usually we have three type of equations that we want to define, or three classes of partial derivative equations. Elliptic equation, and example of the elliptic equation will be the Laplace equation. And this type of equation does not include any derivative with respect to time. And also the second type of PDE equations are a parabolic equation, and this usually include time variable with first order derivative here with respect to time, and second order derivative with respect to space. Okay, so this is parabolic type. And hyperbolic type, it's a wave equations that's usually used to study the microwave signals. And here we have second derivative with respect to space, and we have second derivative with respect to time. So this is the difference between the three type of equations. So how we can classify? Usually we classify by using the formula, the quadratic formula, to classify the equation, otherwise elliptic. If the value of the quadratic is less than 0, that means negative. The second type, if we have parabolic, usually here we have b equals 0 and one of a's and c's are zeros. Or this term, b square is equal this term. So in this case, we have parabolic. These types of hyperbolic, usually a or c are zeros. So in this case, and b is positive or negative. In this case, this will be positive because b square here. So the type here is hyperbolic. After that, we talk about elliptic equations, how we solve the elliptic equations, and we said the basic way we just apply finite difference. So we have three types of finite difference, otherwise forward finite difference or backward finite difference or centered finite difference. And we studied this in Unit 7, and we saw that centered divided difference usually provide a good accuracy if we compare this with the backward and the forward. And after that, we take Laplace equations as example of elliptic equations. That means we talk about elliptic equation solution, and we take example of the heat transfer in a heat plate. And if we have, for example, this is a plate, heated plate, and this is plate, it has a boundary fixed. The temperature at the four sides are constant or fixed at the steady state distribution. After that, we can divide this plate to subgrades, small grades like this one. And from these grades, we can compute the temperature at any node. For example, this node 1, 1, by knowing the values of these subaround nodes, or the temperature at subaround nodes like this one. So for example, for node 1, 1, we have two knowns and two unknowns. So we continue like this one to compute the temperature at all the inner nodes. After that, we can use any Gaussian elimination method to find the solution of this temperature. So usually if we have second order, we represent this by finite difference, otherwise by using centered or backward or forward. So we use different methods here. We start with centered divided difference. We represent the second order by centered divided difference. After that, we assume the distance or the tip size in both sides are the same. After that, we get the general equation for Laplace or elliptic equations. So, for example, for this type, we are interested to compute the temperature at this node for minus 40 Ij. So by knowing the temperature of subaround nodes, these nodes are subaround to the nodes that we want to compute. This is subaround nodes. Usually we have two knowns, two unknowns, sometimes three unknowns. Okay, so in this case, we need to find the temperature or equation for each node. After that, we put them in a matrix form, and then by using the temperature of known nodes, for example, this is constant, and here we temperature here it's are constant, here are constant, and here constant. After that, we substitute in the equation to get a matrix of unknown equations, and after that we eliminate or use any Gaussian elimination to find the solution of these temperatures. This is the direct method that we use to find the temperature of sub or internodes for elliptic equations. After that, we talk about another method, because as we said in this type of equations, if we have 10 nodes, 10 by 10, so in this case we need 100 equations. For example, for this type of plate, if we divided this one based on the step size and we have 9 nodes 3 by 3, so in this case we have 9 equations. So the solution of this one, because we need to define an equation for each or for every node, so as a result we can get a matrix 9 by 9 because we have nodes 3 by 3. So in this case, so this will be the matrix that we have. So in this case, we need to compute the temperature for 9 at 9 nodes. Okay, and this is usually difficult, but if you talk about grades 10 by 10, so in this case we need 100 or matrix with dimension 100 by 100. If we increase 20 by 20 nodes, and you imagine how many nodes that we have. So to avoid this difficulty, we can use the Lippmann method. Lippmann method or Gauss-Seidel method, which is the most common used method in research. This method, no need here to write the equations directly in this form. After that, we have majority of the temperature unknowns. In this method, we assume some temperatures for the nodes. We assume, for example, we start when the temperature at these nodes, at these inner nodes, are zeros. After that, we take alterations. So we rewrite this one, the temperature at this node Tij, it's equal the average of the temperature of sub-around nodes. After that, we update the value of the temperature here at this Tij by using over-relaxation method. And here we have lambda multiplied by the nu equal 1 minus lambda all temperature. So the all temperature we computed from here, or we start from the initial values. So this is the new series. This will be comes here as a new, and this will be from initial value, and usually we start from zeros. All the inner nodes are zeros, and lambda equal 1. Lambda equal 1 to 2. This is the maximum. Minimum 1, maximum 2. So here we have between 1 and 2. So when we stop, usually we stop based on the criteria. Stopping criteria here when the values of the errors is less than a certain value. So how we do this one, ya shabab? Just we start with the average here. We compute the average at this node, and then we use over-relaxation unit. This is the equation of over-relaxation, and after that we update this node. Okay, so this is the new value that we compute here, multiplied by lambda 1.5, 1 minus lambda multiplied by the old 0. So now we update the temperature for all the nodes. We get this one for the first alteration. the first alteration, usually we get the error equal 0. So as a result of this one, we need to take another alteration. So now these results now becomes the old values of the temperature at the old for the second alteration. We have now new old temperatures, not zeros. Yes. Which one?
كيف حسبهم القيم هذه؟
Yes. Here, if you want to talk about T11. Okay, T11, in T11 what we need, here you can see I is 1, J is 1. So just substitute here. So T1, so here this become T2, 1. Okay, so this is because here I1 plus 1, so this 2. So here we have T2, 1. This is T2, 1. And we have also T1, 2. This is T1, 2. These, from the definition of Gaussian method, initially all the values here are zeros. This must be initially are 0. This is initially 0. Okay, so this is the first 0 and this is the second 0. Here you have Ti minus 1. So, and I is 1. So you have here T01. Okay, T01. T01 is this temperature here at this node. And the question defined that the temperature at the boundary is 75. Okay, the temperature at the boundary is 75. So here we substitute by 75. This one is Ti J minus 1 and I equal 1, J equal 1. So here we have T0, T1, 0. Okay, T1, 0. T1, 0 is here. This is the node at this point. You directly know if this is the node, take sub around this node here and this node here and this node here and this node here. You take like this one. Take some of them. This is unknown. This is initially 0. This is initially 0, and this is 0, and this is 75. So you take 0 plus 75 plus 0 plus 0 over 4. You take 75 over 4. So this is the value. Now this is the new value that you compute. After that, you substitute in the over-reelection format. Over-reelection format, it's lambda multiplied by the new. So it is lambda multiplied by the new. New is 18%. Lambda is 1.5. So you have here 1.5 multiplied by 18.75 plus 1 minus lambda. So this is 1 minus lambda in the formula, multiplied by the old value of T11. And we said the old value of T11 is 0. We assume the old value for all the temperature here, zeros. This the method is based on this assumption. So here this multiplied by 0. So for all the first step, you multiply here by 0 in the first alteration. So as a result, we have here 28.125. So this is the first one. After that, we go to compute the temperature for this node. You can see the temperature for this node. We need this node here is 0. This node here is 0. The temperature here we have 0. And this one is 28. We computed now. We already computed. So it is 28.125. Okay, so usually we goes from in this right to right, this direction. After that, we start from here. We goes like this. So here we have T21 is equal 0, this 0, and this 0, and this 0, and 25.15. We get it from here. We take average, we compute this one. So this is the new value of this.
Doctor?
Yes.
I'm confused. When can I consider it as 0 or I calculated? I mean T11. If I want to calculate T21, should I consider T11 0 or I calculate T1 before or what?
Yeah, the starting point is from here. You want to start from this one, the first alteration. You start from this node. Okay. When you start from here, so the old value of this one is 0. The old value of it is 0. After that, you update it. Now you update this value. Okay, you update this value. Here, you take this, when you compute this one, you consider the value that you computed here, you update it. When you go to this one, you will take the value you updated for here, for this point. Not 0 after that. But you have to take this direction.
Okay, so we go from the first row from
Yes. Yeah, from the bottom to the right. Return back here from left to the right, and after that from here to the left to the right.
Okay, and we update every node.
Yes, you update every node. You start from the bottom, from row number 0, row number 1, 2, 3, after that. So this is the way. Okay, so like this one. We do it for all the nodes. Okay, so we update all the nodes. After that, we follow the same method for the other nodes. And here, for example, for 3.2 or 3.1, this node, because we compute the temperature now, or this is the update value for T21. If we look here, we have the value of T21. Sub around the others, we did not update it, so these are zeros. And this is boundary value, 50. Here, the node here is 50 boundary. Okay, so this is 0, this is 0 boundary, but 0. So this is 0, and this is 50, and here this is 10, as we computed for the third one. So we do it like this one. After that, we use the over-reduction method. So we do the computation for all the nodes, started from T11 to up to T3. After that, we check the error. Then this becomes now, for the second iteration, these nodes represent what we call this one, the old values. So we do the average, and after that reduction, when we continue until the error falls below a certain value. Any question, Ishma? Okay, so we update like this one. Take 2, compute the equations as alteration until we finalize with these values, because here the error is less than 1.75. So this method we reviewed before in the last lecture, and also another problem usually if we need to compute the temperature for the secondary variables, not only the temperature. For example, if we want to focus on the heat flux, if the heat flux is very important. So a heat flux, we need to determine the angle of the heat flux and also the value of the heat flux or the magnitude of the flux. So this is usually the method. So we compute the flux in x-axis and also y-axis. After that, we compute the magnitude of the flux and the direction of the angle of these flux. So by using here divided difference method to represent the derivative. And after that, if we talk about, if we take the values of the temperature from the previous question, this is the window. So we can use the temperature at these nodes. Okay, for example, at the first node Tii or T11, for example, this equal T21. Okay, T1 and T01. So T1 is this one, 201 is this one. So we have the value here, and this is the value. So we have 33.3 minus 75, this is constant here, 75 over 2h. H is 2 centimeter or 10 centimeter. After that, we compute it in y-axis. So here we have the value here, we have 1, 2, and 1, 0. So 1, 2 is 63.21 minus here the value is 0. So this is 63.21 minus 0. over 2 delta y. So this is the value here of the q y. After that, we compute the value of the flux, and then the angle of tangent, and this is the angle of tangent. So this will go in this direction. So the question is easy here by using temperature of like this table. If we have table like this one, so it is easy to compute the temperature at different nodes. What should be, or sorry, the flux heat or the heat flux at what direction of the flux. As we know, usually the heat will transfer from the hot to the cold bodies because this has high temperature with compared to 0. So you can see the direction will goes to the cold area. Okay, so if the temperature increase, so the angle usually will increase. Okay, so this is what we talk about in the last lecture. After that, we talk about parabolic equations if we are interested to compute the heat stored in an element. And we take two examples. We talk about explicit method, and I think we reviewed the last lecture how we used explicit method, and here we want to consider explicit and implicit methods. So in explicit method, usually the temperature at node n+1, it's dependent explicitly on the on time n. Okay, so here we have the temperature here, or the second derivative at x1. Okay, at xn+1, it's dependent on the temperature at time n. Here n is represented by L. Okay, so this is n or L. So L represents the time, and you can see here this is the equation. So the equation for all the nodes, we compute the values with some values unknowns. So the temperature at xi or at ti+1, it depended on the temperature or the values that's given at time n. Okay, at time n, so at the previous time. So disadvantage of this method, it is easy to compute, simple to implement, and we can use here forward for first order, forward divided difference, and central divided difference for the second order. The major problem of this method used sometimes is unstable. Okay, so we cannot guarantee the stability or the solution, a good solution, for example, at the end. So it is conditionally stable. So this is the problem with this method, but it's easy. It is easy to implement. So if we represent the second derivative using central divided difference, and here we represent the first derivative by forward. So in this case, we can substitute in the equation that we have it before. This is the equation. And then we finalize with this equation. Okay, we finalize with this equation. So here, by giving the value of lambda, and if you want to compute the temperature at these nodes, we start with the inner nodes. We have the boundaries. For example, the temperature at T0 is defined or fixed, and the temperature at T10 or the second boundary also, or the other side of the boundary, are defined or fixed. So after that, we can compute the temperature of the inner nodes. Okay, and here we assume all the values of the inner nodes are zeros. So then we compute, we'll take the alterations. So here we have the value of lambda, and this is one of the boundaries. So at the first alteration, you will see we have the values of the boundaries only. We have temperature at the first node and the last node. The first alteration, while the others are initially 0. So in this case, we get a matrix of, we get the values of the boundaries. For example, the temperature at the beginning and the temperature at the end. After that, we need to take another alterations. We take another alterations. So for the second alteration, when we go, for example, to at T.2, So in this case, this value of temperature will update. These values of the temperature will update, and also the temperature at the boundaries also will update. So we can update the values of the temperature by using these equations, because now we have another values of the coefficients. So we updated them, and we continue like this one, time by time, until we get the values of the error that we want, or we reach, for example, we compute all the values of the nodes, how many nodes that we want, or we, for example, we do it, for example, eitherwise one alteration, two alteration, until we reach how many times that we start. So this time depend, or how many iteration that we take, it's dependent on the time that we want to reach. So for example, we start from time 0.1, time 0.2, time 0.3, time 0.4, how many iterations? So we just compute or update when we reach, for example. Otherwise, we stop it using, for example, the stopping criteria like the error. If the difference between the new and the old over the new is falls below a certain criteria, so in this case we can stop, or we can do some alterations, like for example, if you want to stop when t equal 0.2 second. So this type of question, Shabab, is very easy, because the format is given like this one. This is the format. We just substitute here, for example, at any node, for example, we start from this point, I equal 1, j, for example, 1. Okay, so after that we update, and then, for example, we need I1, J0, or J1, sorry, at the beginning J0. So we have here 1, 0. So we have 1, 1 here because J is 0. This is the first step. Second step, we continue. We take alterations. We update the time. We take from 1 to 2. After that, if you need, we can take from 1 to 3, like this one. Okay, so we go with time. So we compute here with respect to time. So this type of problems, I think this is the easiest type of parabolic types. Difficulties comes with implicit method. Implicit method also it's used here to compute the temperature. Okay, but the difference here, the temperature in the implicit, it's dependent on temperature at Ti plus 1, or at the time temperature at time Ti plus 1. Okay, so in implicit method, if you go to implicit method, the difference here will be in the second derivative. If you look for the explicit, we update the second derivative in TIL here. That means we compute the temperature, or to compute the temperature at the second derivative, it's dependent on the temperature at time L. But in the implicit, it's dependent on the temperature at time L plus 1. That means at future time. Okay, at future time, and both here we apply central divided difference. So by using central divided difference to represent the second derivative, and the first derivative, the first order derivative, usually here we represent the first order derivative by using backward, not forward, by using backward divided difference. So again, we start with the first node and the last node. The boundaries values, we compute the values at the first node and the last node. And after that, by computing the values of the first node and the first node and the last node, we can update the inner nodes, the other nodes that we have between them. How many nodes depended on the step size that we have. So if we have these equations here, we can substitute in the format that we have. So we get this general equation. So this is the equation of the first node, and this is the equation of the last node. Here, this is the temperature is given. The values here is not just a temperature. You can see lambda is multiplied by T I plus 1 TL plus 1. So here this is a temperature. So this value here, f of 0 is a temperature at initial value or at the first node, and this is also this f m plus 1, it's a temperature at the last node. Okay, not a new function, don't confuse here. This is a temperature, the value of temperature. Okay, and this usually is given in the question. Okay, Shabab, so this is the equation for the last, and this is the equation for the second or the first node. So after that, we need to compute the temperature at the other nodes by using this format. So the same criteria that we use, so we just substitute here. So this is the first node, how we can compute the first node. So we use the equation for the first node, and we know the values of the temperature of the function f of 0. This is the value f of 0 because the boundary for the first node is 100 degrees. We have the value here is 100 degrees centigrade. So after that, this is the value. And after that, we substitute by the value of lambda. And again, these unknowns 1, 1 at the beginning, these are zeros, or sometimes we use some values from table. It depended on the table of we use the initial values of the temperature. What's the point of what's the values of the temperature at these nodes? Initially, we can start from them. So the easy way or the sample way, we start with zeros. Okay, we start with zeros. So this is the temperature here for this node initially, and this is the lambda. So the values here is unknown. We have two unknowns, and this is unknowns. Okay, so we have usually two unknowns here and two knowns values. So after that, we just cut this is known, so this will be constant in this case. So multiply them, we get this constant. So we move these to this side of the equation, and we put the unknowns in the left side of the matrix. So after that, we do this for the last node, and we do the same things for the last node. We get these things. We substitute in the equation for the last node because the temperature also for Fm, this is given, and this value is given, and this is unknown. So this term at the right usually are knowns, and this is unknown for the last and the first node. After that, we look for the nodes between. How many nodes that we have between? It depended on the step size. Otherwise, you have 2, 3, or 4. So in this case, the size of the matrix will change. So we'll apply this for the second node and the third node. And because we have here the 4 steps, so in this case, we have 4 by 4 matrix. So we finalize with this one. After that, we solve this equation or this matrix by using any Gaussian elimination method to get the values of this matrix. So we get these values of the matrix. Okay, these values of the matrix. So this is the values of the matrix that we have. So this is the first step. In the second step, we need to do more complex work. We need to do more work. Okay, we need to do more work to update the values. Now we want to update the values of the boundaries. You can see here we need to update these values of the boundaries by using the equation of the first node and the last node. The nodes, the inner nodes, we use it likely this one. Okay, so after that we update this first, the first column. This is for example, this is the solution here, the solution of this one, and this is the solution of the nodes. So now we need to update the left hand. You can see this is the left hand. This is the value now. We need to update it, and this is the value here. We already computed. It's given here. It's more complicated work. It's need more work. So this is the values that we compute, and these values 2.07. You can see here these values we need to update. So what we look now, we look for these values to update these values to the hand side vector. we need to update the left-hand side vector for the next. Okay, we just update the values in the left-hand vector. Okay, so the left-hand vector is updated. You can see this value here. It comes at this side, and this value here comes here. We need to update to the left hand, to the right hand vector. Sorry, this right hand vector. So here not zeros. We need to update the values, and then we also update the values of the first equation and the second equations. So this is updated by using the equation for the first and the equation for the second. We just update the left hand vector, and then you solve the equation again. We resolve the equation by using Gaussian elimination. We get new results like this one, and then we update this one, and we update this one, the first equation and the last equation, and we substitute in the matrix and we solve them. Okay, so the work here in the implicit, it's more complicated. It's not like the explicit, but this method usually it's stable, or we call this is unconditionally stable. So this is stable in all the condition. So there is no condition for stability here. So the first step, we apply implicit method, and this is called, by the way, this is called the sample implicit. Okay, so the implicit method, we apply the implicit method for the first node and then the last node. This would give us this one. After that, we apply the equations or the general equation for the second node and the third node. This is the first step. We get this equation and we solve this equation to get the values of the temperature that we need here. So this will be the solution. After we get the solution of this temperature, so this one, these values, we replace the temperature here in the second or the left side. We update this, the left side vector. We update the left side vector here. So this is the values here, and we update it. So we update for the first one, the second one, the third one, and the fourth one, and then we solve them. We solve the equation to get the new values of this equation. So this is one of the implicit method. And this method usually it's complicated, but it's provide a stable solution. So another method, it's used to solve this implicit method. We call this Crank-Nicholas method. So Crank-Nicholas method provide another solution for the implicit problems, and this type is more acute. So instead here to use centered divided difference to represent the second derivative, it's use here the midpoint. It's take the average to compute the midpoint. Okay, so here to do this one, we compute the derivative at TL plus half. If we look for this method here, both methods that we studied before, the explicit and the sample implicit, are first order time, are first order in time. Crank-Nicholas is second order in time. Why second order in time? Because here we represent the second derivative by two terms, not only one, and we take average. So in the explicit, we represent the second derivative by this form, by central difference. And we, in the explicit, the sample implicit, sorry, we represent the second derivative by centered difference at n plus 1 or L plus 1 and 2h. So this form that we use it here, it's like a centered divided difference. It's used both to compute the second derivative in space with respect to time L, plus the second derivative with respect to space in time n plus 1, here L plus 1, and after that we average them by multiply these by 1/2. So in this case we don't have direct centered, so we can say this is like centered divided difference. It's not the same centered divided difference, it's like centered divided difference. So as a result here, we have this second derivative and this the first derivative. After that, that means we use here compute the time at L plus half. We take half step. Okay, so we take half step. So if we substitute them by this format in the equation that we have for parabolic equation, we can finalize with these equations. So in this equation, we have 3 knowns and 3 unknowns. Okay, 3 values knowns and 3 values unknown. So you can see we have here knowns and these values is unknowns that we want to compute. So 3 parameter are knowns and 3 parameter unknowns. So after that, we take the unknowns to the left hand and the knowns to, because this will be constant, to the right hand to build the matrix. Okay, so again, we start with the first, with the last node. So this is the equation for the first, and this is the equation for the last. And we said this is f of 0 is nothing just at the temperature. F n plus 1 is nothing also just a temperature. So by using this Crank-Nicolson method to solve the same problems, we can substitute like this one. We apply that method here. And this method usually is also unconditional stable. That means this method is stable method, and it's provide accuracy better than what we use the sample method. So we just update the matrix here. After that, we solve the temperature by using any Gaussian elimination, and then we change the second side vectors. We update the second side vector by substitute by the values that we have in the equation to update the value here. So this is the values of the after updating the left side vector, and this vector must be changed, and then we resolve the matrix to get updating like this one. So we take it for alteration and we stop. And usually these provide less alterations because this is more accurate than what we have in the sample implicit method, and it's provide a good accuracy. Let's check here in this table. This table represent the accuracy, how much these are accurate for solution of the temperature. If the solution, for example, the exact solution or analytical solution is 64.8 or 18, so by using the explicit method, if the step size is high, you can see the error is huge with the explicit method, and here it can be a little bit in the implicit method, sample implicit, and also crank method. If we reduce the step size, so in this case we can enhance the accuracy. So if we reduce the step size here becomes 5 seconds, and the value of lambda also will reduce. So you can see here at explicit is again is too far. It is easy to compute, but the results is too far. Here, for example, implicit is a little bit improved. Crank, you can see, provide a good accuracy. Okay, the error is around 0.01. After that, if we, for example, decrease the step size, you can see this can converge, for example, to minimum errors after, for example, when the step size becomes 0.2, 0.5. While, for example, crank methods provide a good accuracy. Otherwise, with acceptable step size, it's provide a good accuracy. While here, for example, the explicit, the result here is usually unconditional. This is conditional method. So the stability here is the problem here, or the problem with this method usually is unstable. Okay, but implicit are stable. Both are stable, implicit and crank implicit method. And crank is to enhance the accuracy of the sample implicit. So this is the end of this material for this course.